So let's get more into what Phanerozoic marine diversity looks like and why. So here are two examples of diversity curves that have been made over the last 150 years. So the one on the left was made by John Phillips. He produced the first estimates of Phanerozoic diversity in 1860, based only on the British fossil record. And it's actually pretty impressive. He picks up the PT and the KPG pretty well. However, if we look to the right here, we have a very different type of diagram. This is a sample standardized diversity curve made using the Paleobiology database. And so we're going to talk about how we've moved from the figure on the left to the figure on the right. And then we'll continue to talk about how the figure on the right has since been revised by some authors to actually look a little bit more like the figure on the left again. Okay, so in between these two things, we have the famous Sepkoski curve. So Jack Sepkoski was the first person to really analytically analyze the fossil record in a detailed way. He spent about 15 years compiling a database to produce the classic diversity curve that we've seen a few times in the course already. Here, what you're seeing is the marine families, and it's showing the Cambrian, Paleozoic, and modern fauna. So what do we see when we look at this family level curve? So this is a figure also by Sepkoski, but also co-authored with Raup, the guy who did the snail thing. So we see the Cambrian explosion here. We see the Ordovician radiation, what's called the Paleozoic plateau, and then this big rise in diversity in the Mesocenozoic. And then, of course, we also see our mass extinctions, the late Ordovician, the late Devonian, the Permo-Triassic, the End Triassic, and the Cretaceous Paleogene. So another important point here is that diversity depends on your point of view. So here we see the generic level curve. Again, the little arrows are showing our big 5 mass extinctions. But if we move up to families, much of the signal in this curve goes away. We still see the End Ordovician. The End Devonian sort of disappears. The PT, the Triassic, Jurassic, and the KPG are still visible. If we go up again to orders, it's much harder to see basically any pattern. And that's, of course, because when we think about extinction, it's much easier to make a genus go extinct than it is to make an order go extinct. And so what we see at the order level is that orders are increasing as we move through the Paleozoic, and then they're basically steady through time. And we'll talk about this a little bit later, too, about why we don't see more orders originating through the course of the Phanerozoic. And then we've got our big 5 mass extinctions. So this is just a slightly different version of the Sepkoski figure by Baumbach. So it also shows the other names for the mass extinctions. They're often named by the very last stage in the period. So if you see these terms, don't get confused. It's basically just the same thing. The End Ordovician is often sometimes called the late Ashgilian. And then we also see radiations in this. So we've got our Cambrian-Ordovician radiations. We've got radiations basically after each of our mass extinctions. So after the Devonian, after the Ordovician here, after the PT. And then we've got this huge Mesozoic-Cenozoic radiation, which we'll come back to a little bit later, because there's often been discussion about whether or not this radiation is an artifact or if it's real. Okay, so why does it look this way? So we can ask the question, how well does variation in sample diversity match variation in true diversity? So basically, how well does this counting match with what we think actual diversity look like? And we come back to our friends, the biases. So one is the amount of rock available for sampling, which has, of course, changed through time. One is the amount of sampling that actually conducted, because the only things that make it into these databases are fossils that have actually been collected by a paleontologist. Paleolatitude may have a factor. Degree of lithification, so it's easier to pull a fossil out of a poorly lithified or sort of loosely put together rock than a really hard rock. This thing called pull of the recent, which I'll talk about a little bit later. Environments that are represented in the rock record, so we've talked about this already, the bias is there, and then obviously the preservability of organisms. So let's talk briefly about rock available for samplings. This is a little bit like what we talked about with the Peters and Heim paper. So there's a broad correspondence between diversity in the exposed area of sedimentary rocks. So here's our Sapkowski curve, and then this is Raupp's attempt to basically look at the amount of rock available for sampling. And so he noticed in the late 70s that this reproduces some of the Sapkowski curve. And that more rock area sampled will tend to produce more diversity, even if true diversity was unchanging. And so this was a big concern for a long time. Some of the work that Shannon Peters and others have done have alleviated many of these fears, as well as some of the sampling techniques that I'll get into a little bit later. Degree of lithification. So again, it's much easier to pull like this clam out of this really loose rock than to try to extract, say, silicified fossils out of a really, really hard rock. So things that are uncemented or unlithified, you're more likely to find more fossils in. And we'll actually see some examples of this in our field trip. And then this thing called pull of the recent. So what's the pull of the recent? So here we've got our range taxa. And imagine the little red stars are living taxa. So because living fauna are so well known, the ranges of many taxa are artificially pulled to the recent, and diversity is inflated. So if we pull the ranges of our fossil taxa in the blue lineage up into the present, so imagine we have a fossil record, and we're missing it for a long time, and then we have a modern representative. So we fill in that space in between the red star and the blue lines for these taxa, and our diversity looks like this. And so you can think of it as basically the recent having a perfect fossil record. It is the best Lagerstätten ever, and that's going to bias our diversity because Lagerstätten are going to be unusually well preserved and thus have an unusually high diversity. And so there's a concern that this pull of the recent is responsible for some of the inflation in diversity that we see in the Cenozoic, for example. So if we just look at the bivalves over the last 100 million years, if we actually go and look at this, so the black line is with the pull of the recent and the dotted line is without it. So the pattern doesn't really change, actually. It's just the magnitude. And so while this is something to be aware of, it's definitely not a deal breaker when we look at global diversity. Okay, so how can we get around some of these issues a little bit more systematically? And one of the ways we can do it is through alpha diversity. So remember, alpha diversity is looking at within community diversity instead of global diversity. And so in the late 70s, Richard Bombach basically went through and created a table of mean alpha diversity in marine environments that were similar to each other, so open marine environments, so they were comparable. And those are the numbers here. And so you can see the blue is the Paleozoic, the green is the Mesozoic, and the yellow is the Cenozoic. And basically what he saw was that these numbers increased through time, and that the within assemblage diversity in the Cenozoic was truly higher than the within assemblage diversity of previous intervals. And so this suggested that the global curve was actually telling us something primary, because local diversity is not subject to rock area bias. That bias lowers apparent beta diversity, not alpha diversity. And so there's this consensus paper written in 1981 where Sapkowski and Bombach and Raupp and Jim Valentine basically got together and said, look, global and local trends are the same, they're not subject to the same biases, therefore the overall trends that we see in the fossil record are real. So this work provided powerful support for the global curve, again, because local diversity is not subject to the rock area bias. And these guys all agreed that diversity did increase from the Paleozoic to the Cenozoic. Okay, so fast forward to the Paleobiology database. So Sapkowski and all these other guys, their data only included first and last occurrences. It didn't include occurrences in between. So with all occurrences known, you could standardize to minimize the effects of variation in sampling intensity on perceived diversity change. And this is exactly what was done with the Paleobiology database, and I'll explain a little bit more as we go on. So you've already seen the PBDB, you know what kind of information is included. Here's just a list of things that are included. So not only are fads and lads included, every single occurrence is included, depositional environment, mode of preservation, etc., etc. So there's a lot more information included in this database than was included in Sapkowski's original database. So if we look at the PBDB data versus Sapkowski's data, so the PBDB data, just their raw diversity data, is in black, and Sapkowski's is in the thin line. So they're pretty similar. There's some subtle differences, but they match up pretty well. So here's the current coverage of the database. You've already seen it. It's pretty much global. So what John Alroy and others did was they took all of this data and they decided to standardize it in different ways. So one of the ways they standardize it is they said, for every time bin, we're going to take out the same amount of data of the database. So the same sample number, same number of fossil collections, and look at how many species there are in that like grab bag of data. And this is supposed to overcome heterogeneities in the amount of data available, like rock sample bias, researcher bias, people focusing on time intervals like mass extinctions over others, etc. And then they made a diversity curve using this subsampled data. And so this is what their sample standardized diversity curve looks like. I showed it to you in the beginning. This is from 2008. This excludes unlithified sediments, which compensates for the pull of the recent. So it's basically excluding extremely well-preserved unlithified recent sediments, which you could argue is a good thing or a bad thing. So again, here's the standardized version versus the raw data. So they look pretty different. And you can examine this a little bit more closely. So it's harder to see some of the mass extinctions. The Permo-Triassic still stands out pretty clearly, but the Endordovian is much harder to see, and those vertical lines there are error bars on their data. So within error, a lot of the small-scale patterns go away. The PT still seems to definitely be a real thing, as does the Triassic-Jurassic. The KPG looks a lot less dramatic as well, and there's an increase in diversity in Cenozoic, but it's much less dramatic than in the raw data. So when this came out, it was pretty controversial. A lot of people thought that it was overly standardized and was actually throwing out too much data and basically ignoring too much data for fear of that data being biased. And so recently, just in 2016, Andy Bush and at University of Connecticut and Richard Baumbach wrote a new paper in Geology where they basically tried to come to a consensus between these two end members, the raw diversity and the sort of super sample standardized diversity. And here's just the unstandardized genus richness curve from Sapkowski. So this is just redrawing the figure that you've seen a bunch of times already. And then here's the standardized genus richness curve from Alroy. So again, just redrawing a version of that figure that I just showed you, a slightly different version, but again, the sample standardized. And what these guys did is they went into the Alroy data and they sort of analyzed why he had made certain decisions about ditching data from the database. And so one of the things that he did was he ditched the marine tetrapods. And in this paper, they argue that wasn't a good idea. So here, in this figure, we have unstandardized genus richness of all marine animals. So the blue is all taxa and modes of preservation. And then the black is all taxa with some temporally restricted modes of preservation excluded. So that would be exceptionally well-preserved recent assemblages, for example. And then B shows you sampling intensity. So we can see that sampling intensity is much higher in the recent. It's also much higher around extinction intervals. Okay, so we have a lot more data leading up to the Permo-Triassic mass extinction because people are really interested in it, etc., etc. Same with the KPG. So, you can kind of get freaked out at the similarity between these two. But then in C, they basically standardized genus richness based on several versions of the paleobiology data set. And so the different colors here, in red, they've excluded tetrapods. In green, they've summed tetrapods and non-tetrapods together. And in this dotted one, which is really hard to see, they halved tetrapod richness to try to account for a bias towards tetrapod preservation because they have more robust bones and things like that. So anyway, the details aren't super important. The point is that they went through, they challenged a lot of the assumptions in the sample standardized Alroy version, and they came up with their own new version. So this is generic diversity.